G'day guys, just doing the part 2 of the data analysis stack, the short answer one. So I'll be going through each of the answers for the 13 questions. If you just want particular parts, just fast forward to anywhere which after further feedback. But if you want, just strap yourselves in and I'll do this test, or this stack. So what we've got, first question, we've got a histogram below that shows the distribution of weights, in kilograms of a squad of athletes. So we see the histogram is in intervals. It's going in like the athletes will fit within a 5 kilogram sort of interval. All right, so the first question, how many athletes are in the squad? We can see on the vertical axis that's the frequencies. So all we're going to do is just add up the frequencies for each of the bars. So if we look at 50 to 55, we've got 1. I'm just going to keep writing all the frequencies. We've got 2. All right, and see how many we've got in total. 3, 6, 10, 12, 18 up here, 13, 95 to 100s, 4, and 1. Cool. So we're just got to add up those numbers. I'll have a crack in my head. 3, 6, 12, 22, 34, 52, plus 13, 65, plus 5, 70. Cool. Describe the shape of the histogram. We can see that the shape, more of the data is skewed towards the right end of it. So the shape of it's negatively skewed. All right. Good question with the outlier. Would we have to find whether 50 to 55 is an outlier? I reckon you would have to comment on that for the shape. But finding it, you'd have to put in, like the frequencies, you'd have to put in the middle of each of the intervals. So if it was like 50 to 55, you'd do 52.5. I reckon for this 1 mark question, they wouldn't expect you to do that. It might say and comment if there's any outliers as well. But at this stage, I'm not sure if that 50 to 55 is an outlier, but I reckon for the shape, you can just write negatively skewed. I'd probably ask you to comment if there was outliers, and then you'd find it, whether that 50 to 55 one is. Question C, find the percentage of athletes in the squad with a weight between 70 and 80 kilograms. Express your answer correct to 1 decimal place. So between 70 and 80, we've got the 6 and the 10. So that's 16 athletes out of the total of 70. Times that by 100. If you haven't watched any of the other videos, I can't put the CAS on this, so I just do it in the background, but I try and describe how I do it. But just going into the CAS, 16 divided by 70 times 100. And control enter, and I've got a percentage. Just be really careful. Make sure you're reading it. All right, express your answer correct to 1 decimal place. So I've got 22.85, so 22.9%. Cool, moving on. Question 2, the heights in centimetres of athletes in another squad are normally distributed with a mean of 176, and a standard deviation of 5 centimetres. Find the standardised height, or Z-score, for one of the athletes who's 172 centimetres tall. So you could use your summary journal here. What we've got to do is find the Z-score. There is a rule for finding the Z score or the standardized score, it is the actual score that someone got minus the mean divided by the standard deviation. Okay, so in this case, I'll do a bit of working. We don't know the Z score. The actual score of an athlete was 172 centimeters. The mean we were given was 176, and divided by our standard deviation was 5. Cool, so I'll just whack that in my calculator as well. All right, we're gonna get a negative Z score because this athlete's below the average or below the mean. All right, so we get a Z score equals negative 0.8. Cool, I'll just highlight the answers as I go. I should do that from now on. Okay, another athlete in the squad has a standardized height of 1. What percentage of the squad would be shorter than this athlete? Okay, if the athlete has a standardized height of 1, it means it's 1 standard deviation above the mean. Okay, if it's a standardized height of like 0, it means it's at the mean. Okay, we were told what the mean was again. It was 176. I'll highlight it up here. So if they were 1 standardized height above, that means they were 5 centimeters above that. So this athlete was 181 centimeters tall. Okay, so if you want to refer to your summary journal for this, that's that normal distribution chart. Okay, we know the mean is 176. Okay, this athlete's 1 standard deviation above at 181. Okay, and then it asks what percentage of the squad would be shorter than this athlete. Okay, so we want the 50% here below the mean. All right, and also the percentage in that section there as well. All right, so off the top of my head, I shouldn't do this off the top of my head. It's like, is it 16%? I'll just double check quickly. I'm pretty sure it's 16. Where is 16 or is it 17%? Z scores, normal distribution. Wrong, it is 14%. No, 14%. 34%. Oh, I was way off. Okay, so it's 34%. So I've got to add the 50 less of the mean, and then within 176 to 181's 34%. Cool, so you should have that in your summary journal with the percentages there, guys. So 50% plus the 34% is 84%. Cool. So definitely something like in your exam, you could quickly refer to that normal distribution chart. All right, question 3. The following display shows the percentage distribution of sport won by home team or visiting team. Okay, so we've got 3 sports there, baseball, hockey, and basketball. Okay, home team is the lighter violet lavender colour. Okay, and then the visiting team is the maroony colour. So we can see that the home team, for most of the sports, will have a higher percentage than the visiting team. Okay, baseball's pretty similar. Okay, question A, in which sport has the home team won the most? Okay, so that's just looking at that lavender, that'd be basketball. Cool. All right, what type of data is represented in the graph above? Okay, so we've got some categories with the basketball, hockey, and baseball. And then you think, oh, maybe it's numerical because it's like there's percentages and stuff in there. But what it is, it's just either a win or a loss. Okay, so we're looking at categorical data because it's whether it's a win or a loss within those sports. Okay, they're just accumulating the frequencies and getting it as a percentage. Okay, but it's still categorical data. That's represented in the graph above. Okay, you can see frequency tables and percentage bar charts for numerical data though. Okay, often you'll see it within ranges though. So you might see it in intervals. Okay, so intervals of 5, intervals of 10. Okay, it might be student heights. Okay, from 160 to 165, 165 to 170, so on. Okay, so you can actually have numerical data with frequency tables and percentage bar charts, percentage distribution charts as well. Cool. All right, moving on. Question 4, the weight in kilograms of 20 of the athletes together with the time in seconds they take to run 400 meters as shown in the scatter plot below. All right, a least squares regression line has been fitted to the data. Okay, so what we can see, guys, is there's a general trend as someone's weight increases. Okay, there's a general trend that their running time, okay, to run, this 400 meters, okay, is decreasing. And that's shown just by the regression line. Okay, we've got an equation as well, which is predicting the time from someone's weight, okay? What this equation's saying is that someone's time will be 75.95 seconds. Okay, and every kilogram of weight they add on, their time will decrease by 0.29 seconds. Okay, we've also been given an R value there. Okay, so it's a it has moderate strength. Okay, and it's a negative correlation there as well. So as weight increases, time will decrease. Okay, the correlation coefficient, what is the explanatory variable? Okay, explanatory variable is whatever's on the x-axis, so the weight will explain someone's time, so that is the weight in kilograms. Determine the median time of the 400 meters race to the nearest second. All right, so with the median, guys, we're only looking at, for the median time, we're only looking at the vertical dot. So what we're going to do is we're going to start at the very bottom dot, okay, and then work our way up to the top. We have 20 athletes. Okay, so our median is going to be, 20 plus 1 divided by 2. Okay, so it's going to be in between the 10th and the 11th. All right, so what we're going to do is we're just going to look at the dots, okay, and the median time, all right, it's just going to be between the 10th and 11th dot in the vertical axis. So here's our bottom dot, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 10 and 11 are at the same heights there. Okay, and we can see that's at 56 seconds. All right, so the median time is 56 seconds. All right, describe the relationship between the variables time and weight by making reference to the strength and the direction. Okay, so that's where we look at our R value here. Okay, if you want to look in your summary journal, you should have that little coloured printout. Well, it's like a little table that describes the R value and the strengths. Okay, so you'd be looking at the interval that has negative 0.67. Obviously, the direction is negative. All right. And the 0.67, that would be a moderate strength as well. Just be careful, guys. The key word in this question is the describe. Okay, so you can't just write it's a negative, moderate, negative direction, okay, with a moderate strength, okay, because it's not actually describing the relationship. You have to form that sentence. So you could say that there is a moderate linear and negative relationship between the weight of the athlete in kilograms and their time in the race. Oh, that's not a time, sorry. In the race. Cool. All right, moving on. Using the least squares regression line equation, predict the time in seconds an athlete with a weight of 90 kilograms would take to run 400 meters correct to 2 decimal places. Okay, so what we're going to do, we know that the weight of the athlete's 90. We're going to sub that into this equation up here, okay, just to find the time. So it's going to be time equals 75.95 minus 0.29 times the weight of 90. Okay, and it wants it to 2 decimal places, so I'll quickly just whip that up on the calculator. All right, so the 2 decimal places, the time the athlete's going to get is 49.85 seconds. Okay. All right, and then it says explain why this prediction is probably not reliable. Okay, we had a few people say it's probably not reliable because there's a moderate strength, okay, in the relationship, which is sort of true. The first thing you'd look for, though, okay, is just to see if this value of 90, okay, is extrapolating or interpolating. Okay, so if that 90 kilograms, if we go back up to the weights, okay, we can see the 90 kilograms up here. Okay, we don't actually have an athlete in the study that's 90 kilograms. Okay, so we are extrapolating. We're predicting beyond the data we've been given. Okay, so that's the first thing you'd say and why it's not reliable. If, like, we had a weight, within 60 and it said explain why it is or isn't reliable, you could probably say, interpolation it is because it's within the data, okay, but the relationship only still has a moderate strength sort of thing. But yeah, in this case, we're extrapolating. As the 90 kilograms. All right, and because it says explain, don't just write extrapolating. Is beyond the range of weights used. You could write that a number of ways. Question E, find the percentage of variation in the time taken for an athlete to run 400 meters that can be explained by the variation in the weight of the athlete. Express your answer as a percentage correct to the nearest whole percent. Okay, if you ever see that sentence, like find the percentage of your response variable, okay, that can be explained by the variation in the explanatory variable, okay, you're going to be looking at your R squared value. So your coefficient of determination. So we don't know what our R squared value is. Okay, we do know that our R value above is negative 0.67. Okay, so you're just squaring that value. All right, so it should be positive. We always have positive R squared values. So if you get a negative, just ignore it. So 0.4, and what's it want it to? The nearest whole percent. All right, so I've got 0.4489. Okay, which as a percentage, you move that 2 decimal places to the right, is 44.89. And again, because it wants it to the nearest percent, all right, that's 45%. Cool. All right. Okay, the athlete who weighed 73 kilograms ran a time of 53 seconds for the 400 meters. Find the residual value for this athlete if the least squares regression line is used to predict her time for running 400 meters corrected to 2 decimal places. Okay, so if you're trying to find the residual, guys, you've got that equation. The residual equals the actual value minus the predicted. Okay, in this question, we're trying to find what the residual is. We were given the actual time for the athlete. Okay, so that was 53 seconds. Okay, and we've got to find the predicted, okay, by using the equation above. So we're going to have to sub the 73 kilos for the weight back up in that equation to find what the predicted time is. So I'm just writing that equation above. Time equaled, what was it, 75.95 minus, was it 0.29? 0.29 times, and the weight was 73. Okay, so this will give us the predicted time from the regression equation, minus 0.29 times 73. Okay, so that equals 54.78. Okay, so that's our predicted time. I'm going to put that back up the top for our predicted, so 54.78. Okay, so if you do that in your calculator, all right, you get negative 1.78. Okay, and it wanted it to correct to 2 decimal places, so that's our answer. Cool. All right, moving on. Question 5. Okay, the table below shows the monthly seasonal indices for the average number of hours spent training by squad members during 2012. Okay, the entry for September has been left out. Okay, so we've got all the months and their seasonal indices. Okay, complete the entry for the monthly seasonal index for September in the table above. Okay, so if you add up seasonal indices, it should equal 12. Okay, so to find this missing one, you can do 12 minus all those values. Okay, which I'll quickly add up now. Or you could just add up all those values, see what's left over to get 12, which is probably what I'll do. 0.7, 0.8. So if you want to skip ahead, that's fine. 1. This is, again, probably a question you just do again at the end. If you've got a bit of time, just make sure you write all the values in correctly. Like if you ever have data with where you're inputting a lot of numbers, and you have 20 minutes at the end. All right, just redo these questions again, okay, because there's nothing worse than making a little mistake. All right, so I've just added all those values up. I've got 10.8. Okay, so I need 1.2 to get that seasonal index of adding up to 12. All right, in March 2012, the average number of hours spent training by squad members was 20 hours. Find the deseasonalized value. The average number of hours spent training by squad members in March. Okay, so if you're trying to find deseasonalized value, guys, you can, if you want, refer to your summary journal, or if you know it in your head, the rules deseasonalized, deseasonalized equals actual. All right, and then divided by the seasonal index. Okay, so we want to find the deseasonalized value. We know the actual value. Okay, the average was 20 hours. Okay, and for March of 2012, we've got the seasonal index there of 0.8. Cool, so that's going to equal 20 divided by the 0.8, which is at 24. Yeah, 30. 30 hours. Cool. Explain what the monthly index of 1.2 means in terms of the average number of hours spent training by squad members during July. Okay, so 1.0, guys, means it's right on the average compared to the rest of the months. Okay, so if you're ever 0.1, 0.2 above, okay, that stands for like 10%, 20%, so on. Obviously, if you're below 0.9, 0.8, okay, you're below the average by 10, 20%, okay? So the average number of hours spent training in July, okay, for the squad members was 20% above, okay, the average compared to the rest of the months. All right, it says explain, just sort of make sure you write a sentence rather than just like it's 20% above. Like, it's the average hours spent. I hope you have neater writing than mine. It's not the greatest. Hours spent training during July was 20% above compared to the average, I'll just say. All right, moving on. Okay, I got to say I enjoy the short answer one more than the multiple choice. Just like if you know your stuff for the topic, I just find the multiple choice throws in more curveballs. Just more easy marks to get in the short answer. But like obviously if you don't know your stuff, then it's gonna make it harder. But it's been good so far. So question 6. Got the age in years at which a group of 16 elderly people left school. Okay, was recorded. Okay, the data is shown in a frequency table below. Okay, so we've got the age ranging from 9 to 19 years, okay, and the frequencies at which those people left school. All right, what is the mode for this distribution? The mode's the most frequently occurring number, okay, which happens at 11 years of age. Okay, an incomplete box plot was constructed using this data and is shown below. Okay, the line indicating the median has been left off this block, of this box plot. Draw in the median line for this data on the box plot above. Okay, so what we've got to do is you can either do this tech free, or if you want to put it in the CAS, you can do that as well. What will I do? I might do it without the CAS, but okay, if you wanted, you just do it in lists and spreadsheets, but we know we've got a total of 16 members here, guys. So to find the median, okay, I'll just do a bit of working over here. That's going to be 16 plus 1 divided by 2. Okay, so that's 17 divided by 2 is 8.5. Okay, so the number in between 8 and 5, the average of that is going to be where our median should be. Okay, so I'm just going to use these frequencies to count. Along, so that's 1 frequency. Okay, another 2 makes, so 3, 7, all right, 8 and 9. Okay, so our median is like 8 and 9 are both at 12. Okay, so the average is still going to be 12, so your median is there at 12. Cool. All right, the line indicating the median has been left off the box plot. Draw the median line. Yep. For this data on the box plot above. Using the information from the box plot, determine each of the following. So the interquartile range is just Q3 minus Q1. Okay, so we've got a Q3 here at 14, a Q1 at 11. So 14 minus 11 is 3. Okay, then the range is the maximum minus the minimum. Okay, just taking into account the outliers. Okay, so the biggest number we've got there is at 19, and the smallest number is at 9. Okay, so our values range over 10 values. Question D, the data value 19 has been shown as an outlier on the box plot. Use an appropriate calculation to explain why this is correct. Okay, so there is a rule for finding outliers. Okay, if you want to refer to your summary journal for something like this, you can. If you remember the rule, that's fine as well. So we're looking for an upper outlier, because that 19 is up the upper end. Okay, so just make sure you use the right rule. So that's going to be Q3 plus 1.5 times the IQR. All right, so we had our Q3 before, was it 14? Yep. So it's going to be 14 plus 1.5. Now IQR was 3. Okay, which equals, it should be, what, 18.5. I'll just quickly make sure. 14 plus 1.5 times 3. Okay, equals 18.5. All right, so don't leave your answer just as that. All right, because it wants you to explain. If you wanted, you could just say, therefore, 19 is above this value. Value outlier. Cool. All right, moving on. All right, question 7. A similar but larger survey was conducted where adults were asked their age in years when they left school, okay, together with the location of the last school they attended. All right, the results expressed in percentages are shown in the table below. Okay, so we've got the age when they left school, okay, and then comparing that with the location, so urban, regional, or remote. Okay, so question A, of those who last attended a regional school, what percentage left before the age of 18? Okay, so key word there being before, and also that we're looking at regional schools. So we don't want to actually include the age of 18 in regional schools. So we go to regional. That means we want 17, 16, and 15. Okay, of those who last, what percentage is left before the age of 18? Yep. So, and then just add those 3 percentages up, which is 27.6 plus 31.4 plus 19.5. Cool, so that is 78.5%. All right, question B, explain whether or not the data supports the idea that there is an association between the age at which a student leaves school and the location of their last school. Okay, use appropriate percentages from one age group, okay, to justify your answer. All right, so what we want to do, guys, is either answer's correct, okay, if you can justify it. So we want to know whether at certain age groups, do people leave school at different age groups depending on where they went to school? So, at urban areas compared to regional, compared to remote, is it the same or is it different? All right, so what you want to do is just make that, or you can make a judgment by looking at the percentages and what you think. Again, whichever way you go, as long as you can sort of really justify it. For me, like if I just look at ages when leaving school, like obviously generally people leave at 17 and 18. Okay, if they finish their schooling. Okay, anything before that just means they haven't sort of done their VCA. So if I even just look at age of 15, what you're looking for is you're looking for differences. Okay, you see if there's any major differences. Okay, if the percentages are the same, all right, then there's not going to be any association between age of leaving school and their location. But just looking at 15, we can see in urban areas, only 16.2% of school children will leave at that age. Okay, regional is a bit more at 27.6%. And then we see that bigger jump in the remote areas or remote schools with a whopping 40% of kids will leave school at 15 in that area. So just even comparing urban to remote, okay, 16 to 40%, that's a good 24% difference. All right, so for my justification, I'm going to say yes, there is an association. Association between the age of leaving school I spelled school wrong. I forgot the C originally. The age of leaving school, okay, and the area or the location that they attended school. School. Okay, if you're ever justifying, guys, make sure you do include the percentages in it. Okay, so I'm just going to include the urban, regional, and remote percentages. So I'll just say remote at 40.6%. Remote students I should say high proportion of remote students. I might go back. It might not have come up for you anyway, but high proportion, probably a good question to do with a pencil. Of remote students leave school. Leaving school. All right, and just make sure you include that percentage again, so 40.6. At 15 years age. 15 years of age. Compared to urban, to regional. All right, and that percentage was 27.6. And remote. Okay, so again, you don't have to use the percentages that I've used. If you want, conversely, like you can see at sort of the 17, that one I reckon has the most difference. But you could use maybe at age of 17, your 17, your 18-year-olds have a high percentage of the urban students sort of getting or finishing school. We don't know if they're actually finishing school, but at 17, 18 years old. But even if I look at just age of 17 and urban, we've got 30.6% leaving school, 19.5% for regional, and 10.3% for remote. Okay, just comparing urban to remote, it's not as big a difference, but there is a difference, like a 20% difference there in the percentages. All right, question 8. The scatter plot and table below shows the number of internet users signing up with a new internet service provider for each of the first 9 months of their first year of operation. Okay, so we've got the months there. Okay, and then the number of users to the right that are signing up to a provider. Okay, the relationship between the number and month is non-linear. Okay, a log transformation can be applied to the variable number, all right, to linearize the scatter plot. Okay, so it's not too bad, but they've just said that this isn't quite linear. Okay, if you continue on the months, it might become more of a curve, but what they've done is they want to apply a log transformation to the number. Okay, so they want to apply a log transformation to the y, or the response variable. Okay, so question 8, apply the log transformation to the data and determine the equation of the least squares regression line that allows the logarithm of the number of internet users to be predicted by from the month of their first year of operation. Okay, write the slope and intercepts of the least squares regression line. The boxes provided below range answers to 4 significant figures. All right, so what we're going to do, guys, is we're going to put this information into our CAS. Okay, so all right, the month is the explanatory variable. The number is the response variable. Okay, if you think of them like X and Y axes, if you want, or variables, you can as well. So what I'm going to do is go listen spreadsheets and my CAS. All right, I'm going to label the first column just M for month, and the second column N for number. All right, I'm just going to put those months in, 1 through 9. Yeah, and so I'm just doing this on the calculator as I'm saying it to you. So, and then the number, putting that 24 through to 118. 35, 44, 60, 61, 78, 92 and 118. Okay, then I've got what it wants us to do is to apply a transformation. Okay, so in the next column, the third column, I'm just gonna, you can label it whatever you want. I'm just gonna label it T for the transformed one, and it wants us to apply the transformation, all right, to our response variable. Okay, I wanted a log transformation. So what you do is once you've labeled it T at the top of that third column, okay, in that box just below, you can just do control log. Okay, control log. So it's going to look like this, just in this box below. Put 10 in there. Okay, and in the brackets, you're going to use the number there. So I labeled mine N. I've got the E and R. That's just, hopefully it doesn't confuse you, but my number was for N. Okay, and then press enter, and then make sure it's variable reference. Okay, and then what I've got to do is produce a scatter plot. So control I on your CAS, go to data and statistics, number 5. Okay, down the bottom, your variable is still, I'll highlight on here, your variable is still your month. So I've got that as M for me. Okay, your vertical axis, when you do it on your CAS, I've got that labeled as T. Okay, so then you should get your scatter plot up on your CAS, press menu, analyze regression. Okay, and you can show the linear. All right, so, and then you get the equation. Okay, so my one, just the formatting here is stuffed up a bit. But your response variable comes first, so it should be log 10 of the N. Actually, I might even include number. Okay, equals. All right, and I'm not sure which one comes because the formatting's stuffed up, but I'll do the y intercept first. So wants it to 4 significant figures, so 1.314. Okay, and then plus 0.08. There's our first significant figure, 3, 0, 1. All right, there's a 9. That was a 0, but there was a 9 after that, so it rounded it up. Cool. And that's times the month. So that's our slope. All right, question B. Use the equation of the least squares regression line in part A to predict the number of internet users after 10 months. Give your answer correct to the nearest whole number. Okay, so what we've got, guys, now that we've got the equation, all we're doing is subbing the 10 months in for the month up here, okay, and solving for the number. Okay, so on your CAS, if you want, you can just do solve the log 10 of, if you've got it as, you can put it as N just in your calculator, equals the 1.314 plus the 0.08301 times a month. Okay, just going back a step, with significant figures, guys, just remember that zeros are not considered significant, okay, unless they are between significant figures, okay? So the 2 zeros at the start here weren't considered significant. Okay, then I hit the 8, so that's my first significant number, the 3. Okay, then I got 2 zeros, okay? And they were actually between significant numbers because this was like 0, 0, then there was a 9. Okay, so the 2 zeros count as significant. Okay, and then the 9 just rounded that last 0 up to a 1. So hopefully all over significant figures. Okay, just going back, okay, so I've written in the equation, I'm solving, sorry, that month will sub in 10. Okay, and we're solving for n. Okay, so I'll whack that in the calculator. All right, I'll get a decimal answer. But again, just reading the question, making sure you want it to the nearest whole number. All right, so the log will always, you'll always have 10 as your base. 0.08301 times 10, solving for n. Okay, so that comes out as 139.34 users, okay, which to the nearest whole number is 139 users. Sweet. All right, next question. Question 9. The age in years at which 12 adults left school and the age in years at which their mothers left school are shown in the table below. The data is also represented in the scatter plot shown below. Okay, so looking at that, this is the age that the student left school. Okay, and this is the age that the mother left school. Okay, so just looking at that, I'd presume that the mother's age would be the explanatory variable. And, you know, depending on what age the mother left school, in response, they'll be looking at what age the student left school to see if there's a correlation there. All right, so sorry, the question. There appears to be a linear relationship between the variable's age and mother's age. A least squares regression line is fitted to the data. Find the coefficients for the equation of this least squares regression line and write them correct to 3 significant figures in the boxes below. Okay, so done this skill before. Just list and spreadsheets. I'll control N just to clear everything. Just make sure I don't get any mistakes. Okay, I'll put age for the first column. Actually, I might put mother's age. I'll put M first because that's the explanatory variable. And then I'll put A for the response variable. So put that in the second column. Again, it doesn't matter if you write which one you put in the columns, just as long as you get your explanatory and response around the right way. Okay, so I'm just going to put the mother's ages in first, 14, 15. All right, you always want your explanatory variable on that bottom axis, and it's just easier have it in that first column. Stops you from making a mistake. Again, yeah, it shouldn't matter heap if you just know which one your response and explanatory are. Okay, 18, 11, 17, 12, 16. Okay, if you ever need hints, you can just look at the equation given below. We can see that the mother's age is explanatory and this kid's age is the response as well. Okay, 16, sorry, I'm blabbering on. All right, second column, 13, 17. All right, so this should be, you see a question like this, guys, should be easy marks. Okay, the only way you lose a mark here, I reckon, is you just put a value in wrong, which I'm hoping I'm not doing. 13, 17, 15, 17, 16. Again, I probably should be crossing them off as I go. It's a good habit. I've done all these ones, so I'm doing this super slow. But yeah, good habit. 16, 14, 18, 17, 12, Okay, it's worth spending an extra, 30 seconds just to make sure you do this right. Okay, you don't put something in wrong, because that would be horrible. All right, so now that I've put the data in, I've got 12 values for both columns. I press Control I. Data and statistics, okay. On my bottom axis, I've got the mother's age. And in response, the vertical axis, I've got the child's age. Okay, and then to get the regression line, press Menu, Analyze, Regression. Okay, show linear. And you'll get the line in the scatter plot. So hopefully you can picture that as I'm doing it. All right, so I have the values. It wants it to, 3 significant figures. Okay, again, just whichever one you write, when you're doing like the linear, just make sure you put the numbers in the right boxes. Okay, so my slope here, I've got 0 because it's coming up first for me, 0.734. My intercept, 4.25. Find the coefficient of determination for this data set. Express your answer correct to 4 decimal places. Okay, so there is a way of doing this. Okay, if you haven't set up your calculator so that when you do a regression line, you'll get the R² value up straight away. So if you do, that's sweet. If you don't have your R² value just below the equation, in your calculator, just press Menu, Settings, go to Diagnostics, okay, and then just select the default, okay, for all future documents. So tick the little Diagnostics box, okay, and then you should get that R² value all the time. My calculator is dodgy, okay, so I have to get my R² value back with my statistics, so I'll just quickly do that. Stat calculations, 2A variable. X is M and A. Again, if you don't get that, maybe just speak to your teacher about trying to get that set up so you get that R² value each time. Okay, so if we're going to 4 decimal places, that coefficient of determination is 0.6142. Cool. All right, interpret the coefficient of determination found in part 1 in terms of the variables age and mother's age. Okay, so if you want, you can have a template which describes this. So essentially all it is you turn that R² value into a percentage. Okay, so move the decimal point 2 places to the right, and then you say the variation, 61.42% of the variation in the RV can be explained by the variation in the EV. Okay, so if I write that out, so I'll just turn that to percent, and then you just copy that template for the question. So 61.42% of the variation in the RV, which is age, can be explained. Age, I should just write age leaving school. I might go back. Oh, it might not have come up for you anyway. In the age leaving school, can be explained by the variation of the mother leaving school. Cool. So just the percentage of the, I always get mixed around with it. The percentage of the RV can be explained by, or the variation of the RV can be explained by the variation of the EV. All right. And that's all it wanted. Yep. Cool. All right, moving on. Okay, question 10. Following scatter plot shows a relationship between annual income in thousands of dollars and the number of families who own at least one car in Tennyville. All right, so the equation of the least squares regression for this data set is as follows. Number of families equals 53. And every 1,000, their income goes up. It'll increase by 0.47. They have a car. All right, draw this least squares regression line on the scatter plot above. Okay, so the easiest way to do a scatter plot, guys, is just put 2 points. All right, the easiest point to start with is always your y-intercept. So when x equals 0, okay, our y-intercept is 53. Okay, so what's this? 40. What's it going up by? 4s? Is it 44, 48, 52, 56? Yep. So 53 is just above, what's that? 40, 44, 48, 52. There's 53 right about there. Okay, and then to get the next point, guys, what you do is you sub in the last value. So this 120 into the annual income. Okay, so I'll do that now. 53 plus 0.47 times 120 just to get the next point for our line. All right, so if you ever have to do a regression line, guys, do the y-intercept first and then just go to the last point, sub in the value for the x, all right, to find the next coordinate. All right, so it took a while. 53, 0.47 times 120. Okay, I get 109.4. So I'll just try and match this up. That's 100 there. Yep. So that's 104, 108, 109 just above it. Again, my my test is really zoomed out, but once you've put in those 2 points, guys, use a ruler. Do not do this freehand. I will try my best on this. Okay, just draw a straight line. Okay, between the 2 points. Sweet. Okay, my line didn't match up perfectly with that. But yeah, use a ruler. Okay, just to be really accurate. Okay, and that's drawing a regression line. Shouldn't be hard. Okay, but it's something every year people, just don't do right. Okay, question B, interpret the vertical intercept of the least squares regression line in terms of number of families who own at least one car and the annual income. Okay, so essentially the intercept is this 53. What it means is when the annual income is 0, so when annual income is 0, the number of families who own at least one car is 53. Okay, does that 53 Yeah, it just represents the number of families. Yep. C, use the equation of the least squares regression line to determine the average rate of increase in the number of families who own a car in Tennyville. All right, so what it just means is for every time we move across $1,000, okay, so every time, I'm just going to go back up to the equation. Every time we go up $1,000, so we sub in a 1 here, okay, or a 2, I'm just going to 2, or a 3,000, or a 4,000, or a 5,000, okay, the increase in the number of cars of families, or number of families who have one car is 0.47. Okay, so essentially it's just the slope. Sweet. Cool. All right, and that's the average rate of increase. All right, next question. Question 11. A survey results show the following statistics for the number of hours spent by students on Facebook each day. Okay, and then average number of hours spent studying each day. All right, so we've got statistics such as the mean and standard deviation. So the average number of minutes students will be on Facebook is 90 minutes. The average minutes of studying is 135, sorry. Okay, and then we've got some standard deviations. Okay, and the correlation coefficient. So you can expect with these values, it's going to want us to get the regression line, but we'll see what the question says. Use the information in the table below to show that the equation of the least squares regression line for the hours spent studying Y in terms of the number of hours spent on Facebook X is given by. So we've got that equation there. We know what the values are. We've just got to show it. So we need to find the slope, and we need to get the match up to this 1.17. Okay, and we need to find this intercept. Okay, if you're ever doing statistics, guys, you do have to do it in order. So you need to find the slope first. Okay, before you can find the intercept. Okay, so you can have your summary journal for this, but to find the slope, it's correlation coefficient times standard deviation of Y divided by the standard deviation of X. Okay, so that's going to equal negative 1.17. In my calculator, I've just got a fair few decimals. Like it looks like it's recurring, it's going on. So I'll leave it at 1.17. But what I'll do is I'm now going to find the intercept. So the intercept equals the mean of Y minus the slope times the mean of X. Okay, so that's going to equal our mean of Y is 135 minus the slope. So instead of I might just write I might actually include all the decimals. So I had 1.173521. 3521 7391 7391. Okay, times the mean of X. The reason I'm including all those decimals is just so I don't make a mistake. Minus that, there should be another negative in here because it's minus the negative 1.17. So I should have two negatives in there. Okay, so I'll do that on my calculator. So 135 minus negative 1. I'll just quickly whip it up. Okay. All right, so that gets me to 240.42. 4216. Okay, which doesn't quite equal it should be 240. 240.43. What's going on there? Is that a mistake in the sack? $135 plus, yep, because it turns into a plus 1.1735. Where's that become 14? Oh yeah, because I got 135. Ugh, that's where the mistake is. No, I included that 1.17135. I don't think they've made a mistake there. 240.4, 216. Looking at the working, they've provided this as 1.4, so it's been rounded. There's supposed to be a 1 in there. It's been rounded, but it shouldn't have. So this is actually more accurate. Okay. That is interesting. Alright, moving on. Okay, I'll see if I made a mistake there. I can't see one. Because that, if you're using that, that's been rounded. But, as it said, yeah. Interesting. Righto. This following question relates to question 12 and 13. The All Ords Index is the Australian share price index measuring the market price of the major stocks listed in the Australian stock exchange. It is made up of share prices of approximately 500, blah, 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 blah. Cool. All right, so we've got the All Ords Index for different dates. Okay, so what they've done is just plotted that on a time series. So they've got the 15 dates there and what the value of the All Ords Index was. All right. So what it wants us to do is to do some smoothing. So question A, use 3 median smoothing to smooth the time series. Plot a smooth time series on the plot below. Mark each smooth data point with a cross X. Okay, so if we're doing median smoothing, guys, we want the middle number, and it's 3 median. We want the middle number horizontally, as well as the middle position vertically. Okay, so you have to start here at this point at 2, because you need a point either side. Okay, so if we go across horizontally, the point at 2 is right in the middle. Okay, and this point at 2 is also in the middle for the heights as well, so vertically. Okay, and then we're up to at 3, so we go to the left, and again the middle's there. Okay, the middle of the 3. Again, that's the middle. All right, this one's where we first get a change. So the middle is here at this point here, but vertically, this dot here is actually the vertical middle. All right, so that goes there. Same for this next point. It'll go up there. Okay, then it'll, looks like it'll just continue on its trend along. All right, so I'm just going to join those points. Finishing that question before, how you guys go with it. Even looking on your sack, if you did something different to me, or if you just did the working and then said it worked out to be 120.43 and just showed it, and I'm sure you probably got the marks for that anyway. But yeah, it didn't add up for me, so yeah, but I might have done something wrong. Okay, describe the general pattern in all ordinary indices that is revealed by the time series plot. Okay, so the general pattern, we can see an increasing trend. Okay, we can see over the 15 days that increasing trend. So, because it says describe, I'll just write all odds is showing increasing trend over time. Okay, would the 3 median smoothing or 3 moving mean be a better form of smoothing for this data? Explain your answer. Okay, essentially, like, the difference between the mean and the median is that the means can take into account the outliers. Okay, so if we look at the very first dot here at 1, I should use colour other than red, I'll use green. This dot right there down the bottom, if we use the mean, okay, that would have actually been taken into account for the 3 moving mean, but it didn't have an impact when we were doing the median, okay, because it wasn't in the middle, so vertically or horizontally. So the 3 median smoothing. All right, if you ever get asked this question, mostly it's 3 median smoothing is better. As there is an outlier present. At 1, which I'll just write 3 mean smoothing takes into account. We'll use. Cool. All right, last question. It's just showing that it's non-linear. Relationship between the all odds, daily indices, and time appears to be non-linear. Okay, we've got the data there below. What they do is apply log transformation to the variable time. Okay, so time, in this case, for time series, it's always the explanatory variable. Can we use to linearize the data scatter plot? How will a log transformation applied to the variable time affect the data? Okay, so if you ever use a log transformation, okay, that's going to compress the data, okay, or compress that variable. So it's just going to compress the time variables. All right, that's all you need to write. Apply a log transformation to the data, determine the equation. Oh, there's a lot of this in this test. Okay, write the equation in terms of the all odds index and log time. Give the slope and intercept corrected to 2 decimal places. All right, so had plenty of practice of this. You need to go back up to the raw data. Okay, you're going to put these in your list and spreadsheets in CAS. Okay, time is your explanatory variable. This is your response variable. Okay, and then the third one is we're going to have the log 10 of the time. Okay, so I'll just put that as T. All right, I might even give it a capital T, so. And then I'll have to just use make the scatter plot to get the regression line. So into your CAS, lists and spreadsheets. My time, I'm going to label as T. No, I'm not. Because I'll have a transformation. I'll label it as T. It's fine. 1, 2, 3, 4, all the way to 15. Again, just make sure you do this correct. One mistake could be horrible. Okay, I'm going to label my second one just O. Alright, this is... Lucky this is the last question. It's time consuming. 4762. Alright, skip ahead, guys. I'll just whack all these in. 4780. Again, I should be modeling good habits. 4780. Seven nine. 4 8 6. 4 7 9 2. 4 8 2 8. 4 8 3 0. 4 8 3 0. 4 8 3 0. 4 8 4 1. 4 8 5 1. And 4 8 5 3. 4 8 5 3. Cool. Alright, I'm just putting in the next one. I'm just going to label it, obviously not T, just give it B, doesn't matter. All right, so beneath that, go control log to the 10 of, and we're applying it to T. All right, enter, variable reference, okay. Okay, then control I, plot it, data and statistics. Remember, put your log, because it's the transformation of the explanatory variable this time. Okay, so in my case, that was, what did I put it as again? Put it as B. And I put this one as O. Cool. And then what did I want? I wanted the equation. Sweet. Cool. So just make that regression, menu analyze, make the equation. Right, so that regression equation, remember, don't put your y and x there. Use the variables. So in place of y, we've got the all odds index. Okay, so we've got the all odds index equals, and I'm just starting off with my intercept, so 128.28. Okay, my slope, no, that was actually my slope, sorry, times the log of time. Okay, plus 4698.25. That rounds up. All right, last question. Use the transformed regression equation to predict the all odds Index for 17th of December 2010. Show all working. Write your answer correct to one decimal place. Okay, so 17th of December, guys, if we go back up, each of these days here represent the date in December. So it's 1st, 2nd, 3rd, 4th of December. If I go back up, okay, each of those days just represent the 1st and 2nd and so on. Okay, so if December 17th just means we're going to sub in 17, okay, for our time. Okay, so what we're going to do is find what the all odds index is. Okay, so we're going to have to solve for the all odds index. Actually, you wouldn't even have to use solve here. You could just, if you want to, just whack 17 in there for the time. So I'll just rub that out. Yep. All right, so all odds. Okay, got to show working. 128.28 times the log of 17, log 10 of 17, plus 4698.25. All right, we can use the rounded off equation here, guys, because it says, you know, use transformed regression equation. So use the one that we've just made. Okay, so I'm going to quickly whack that in the calculator. And we're done. Just get the answer. So overall, as I'm writing this, guys, there was a lot of, for this short answer test, there was a lot of putting stuff in the list and spreadsheets. Okay, a lot of finding regression equations, that sort of thing. Okay, if you know how to do it, yeah, it should be your bread and butter. Okay, sometimes it can be like pretty time consuming, so just make sure you don't write something in incorrectly. It's really easy to do. So just cross things off as you go, and that sort of thing. All right, so what I've got here, I've got a predicted, it wants it to one decimal place. It's going to equal 4,856.09, so 0.1. Cool, and that's the end of this sack. Thanks, guys.